So for the three in-person presentation, let's start with Keshav Kaushik, who's going to present his paper entitled A Real-Time Non-Invasive Anomaly Detection Technique for Cooling Systems.
Good afternoon, everyone. So today I'm here to present my paper on real-time non-invasive anomaly detection technique for cooling systems. We all want the thermal comfort in our rooms, but it comes up with the expense. It comes up with the expense of energy. So, like the cooling systems consume energy, which is a costly, which comes with some cost, right? And also it also affects the environment. The more energy we are using, the more cooling systems the heat we are using, the more carbon emissions will be there. But to deal with this, we focus on a particular type of problem for energy systems, which is anomaly detection, and we specifically focus on cooling systems. So cooling systems consumes more than 40% of building's energy in a particular building, and because of global warming, the demand of cooling system is increasing day by day. And so in general, we have two types of cooling systems which can be used in our buildings. One is ductless cooling system, and the other one is ductless headless cooling system. So ductless headless cooling system, we have one external unit which is connected to air handling unit, which distribute cold air within the particular rooms. However, in ductless cooling system, we have one external unit associated with a single air handling unit in the room. So each of the ductless cooling system is considered as an individual cooling system or ICS. So there are challenges in identifying the anomalies in cooling systems. So the currently available solutions are human intervention, where you call a technician who will come and they will deploy multiple sensors to check which particular part of the cooling system is faulty. And then this is not like you cannot expand the solution to every building, because a homeowner cannot call a particular a technician because it's a costly. So you cannot call a technician to check whether there exists an anomaly in the cooling system or not. And there are some data-driven models which are only capable to detect anomalies once they have happened and they have already destroyed the system, right? These solutions are also not good enough. So like the data-driven solutions are neural networks and others. So you need a lot of data to deal with that. But this is reality that we don't have a lot of data for each type of anomaly in cooling system or for any system for that matter. So our motivation to solve this is like occurrence of faults or anomalies in cooling system is quite frequent. It's not very rare. It's quite frequent. But these faults cause for more than 45% of wastage in an overall lifetime of a cooling system, which is really significant. And due to inefficient cooling system, like we, so what we want to do is we want to identify whether there exists an anomaly anomaly in cooling system. Because of that anomaly, the cooling system is inefficient. Or are we not aware about what type of anomaly it is if we know that there exists an anomaly? So we don't know what kind of anomaly it is. Is it a human-based anomaly or other category of anomaly, which we discussed right now in further slides? And we are not aware about the cause of the anomaly. We know, okay, there exists an anomaly based on some time series pattern detection. We know that there exists an anomaly, but we don't know what is the cause of the anomaly. So these are the issues due to which we use inefficient cooling systems. So, this is a basic overview of how a cooling system looks. So we have an air handling unit which distributes the cold air in the room, And we have external unit where we have 5 major components. One is evaporator, compressor, condenser, and extension valve. I'm not going to discuss in detail about what these components are. And so this is a our real world setup where we have deployed energy sensors with the cooling system to measure how much energy these are consuming. So we use IoT to solve this particular problem, and these sensors are connected to internet, which help the air conditioner to send the data over cloud. So our solution, we propose a three-stage solution. So our solution takes two input parameters. One is energy rating, and the another one is power consumption of cooling system. And so we have three-stage model. In first stage, what we do is we identify whether there exists an anomaly or not. In second stage, we identify what is the cause of the anomaly, and in third stage, we identify which particular part of the cooling system is faulty, which particular component of the cooling system is faulty. For that, we propose our own machine learning algorithm called NNDVC. So for identifying anomalous events, we use data-driven time series analysis, where we check whether there is a deviation of more than 5% within past 90 minutes. If there is a more than 5% deviation, then we flag it as anomaly. So here, because we have a limited time window, our solution is cheaper, like in terms of time complexity is big of n in our case. Then we identify which particular type of anomaly it is. So we classify anomalies in three categories. One is anomaly cause one, where we say that the user has set a wrong temperature. Like when we say wrong set temperature, we mean like your desired temperature is different and your set temperature is different. These are not correlated because the desired temperature and set temperature is not always same. Then anomaly cause 2 is a technical fault. If we identify that whether there exists a technical fault or not. And the anomaly cause 3 is the cooling requirements of the cooling requirements by the cooling system is not cannot be satisfied now. Because let's say you purchase a system 50 years back and like or not 50 years, 10 years back, and it is not efficient to cool them. To do that, we propose a rule-based methodology where we check like based on what is the temperature deviation based on external temperature and internal temperature. We studied actual guidelines to decide on these rules, and then once if it identifies that there exists an anomaly cause 2, which is a technical anomaly, then we want to identify which particular part of the cooling system is faulty. So for that, we evaluated what is the impact of energy consumption and temperature, how does it correlate with each other, right? So we observe that yes, there is a possibility that we can identify this because we were able to cluster the anomalies for each component using a DB scan methodology. However, we were not able to use DB scan methodology. Why? Because DB scan is an unsupervised approach. Like we cannot use unsupervised approach for identifying anomalies, which is a supervised classification problem. So, for identifying the faulty part, the solutions which exist are probabilistic solutions, where we have some causal-based methods, causal-based models, which requires a lot of data for each particular type of anomaly. And now each type of anomaly is not so common. Like we can have a wrong set temperature could be a very common anomaly. However, faulty compressor could be very rare. So, like we cannot have for each type of anomaly cannot have sufficient amount of data. Then there are some regression techniques using neural networks and also like again the data set is a real problem here. So to overcome these challenges, we propose nearest neighbor density based clustering application with noise. It's a modified version of scan algorithm. So I will discuss what we do here. We estimate the in-center of each 5 components of the cooling system. So what we do is we use energy plus simulator where we model each anomaly for the cooling system. and then we estimate what is the in-center of each particular component, and then we calculate what is the percentage contribution of each component. So that percentage contribution comes out to be the in-center of our new air condition where we want to deploy our solution. So this methodology also enables the transfer learning. So now, if you want to shift to another cooling system, you just need to take energy rating data of the cooling system, then multiply it with the percentage contribution. So you will get in-center for that particular cooling system. Now, and so so now so I've like concluded this part mostly, and then what it will do, it will execute the nearest neighbor technique, nearest neighbor cluster assignment technique to be up to a point where it achieves main points. Where main points are the number of points which is required to enable DB scan to run perfectly. So up to that point, will use nearest neighbor. Then it automatically turns to be turns using DB scan. Yeah. So okay, I think so this should be an animation. Sorry, yeah. So I'll tell you. So we evaluated our solution with five different types of techniques, the classification techniques, which is cat boost, uh, neural network, and DB scan is there, and then DB scan is there, and XGBoost. We observed that our solution, like we deployed the solution in multiple environments, in a lot of simulation environments, in a lot of real world environments, and we shown the results in the presentation, which is not visible right now, but like we shown the results of the worst environment where we observed this. So even in that scenario, our accuracy score was over 0.82, which is quite good in comparison to other algorithms, which were very less. And also our F1 score was also 0.79, which is again quite good, and which confirms that what we are doing is actually in the right direction. Because when we consider other approaches where the accuracy score was near to ours algorithm, but F1 score was really low, which means that they were just predicting randomly and they got lucky in that terms in that case. However, with our solution, our F1 score was quite good, which means that we were able to identify anomaly cause correctly. And so here we also show in six different simulation data how our solution works. So for each stage, we are showing that how much accuracy, what is the AUC ROC score at each stage, what is the accuracy score at each stage, and what is the overall F1 score for the entire system, which is around 0.76, I think. Yeah, 7.76. And the for stage two, because we are using rule-based approach, we always got the AUC score of 1, because those are based on rules, and we designed rules very carefully using the guidelines of ASHRAE. And what we observed is we observed up to 30% energy savings in real world deployments. We observed that early identification of anomalies can reduce the downtime by 75%. This is one of the real world scenario, and if you come to it, it's a very interesting scenario. I can explain you what actually happened, and like yeah, this was really good motivation for us to continue working on this problem. And identification of faulty parts also reduces early identification of faulty parts reduces mean time to repair the cooling system. Uh, that's it. And I'm a final year PhD student, and I have submitted my thesis and looking for academic opportunities. If you have any needs, please let me know. And also, we have like last month we had this Basis conference where we published a paper for the data set which we collected. So if you want to access the data set which we use in our solution and which we have made public, so you can use the QR code for us. Thank you.
Thank you very much, Keshav, for the Nice presentation. So any questions in the room for Keshav? Yes.
Hey, thanks for the nice presentation. In your one of the earlier slides, you showed the different clusters for the components, component-wise clusters, right? And the grouping between them seems to be really very narrow. So I wonder if the DB scan method, if it has some outliers, which it is known for, right? How do you handle that here? Do you run the risk of classifying them because the border points are really very narrow? The distance between separation is really very small.
So that is the reason why we went for density-based algorithm. So if you have used any other type of algorithm, let's say, even for the nearest neighbor technique for the complete equation, then also it won't be able to identify each component because there are some overlaps. And either it is overlapping on the temperature or it is overlapping on the energy. So it's not in both of the cases right. So it is very rare to have overlapping in both of the cases. Obviously, we are not assuring that it is able to 100%. We are not assuring 100% accuracy. However, it is like significantly good because the density of changes when you have two parameters, like energy consumption and temperature. The density of the particular anomaly data point will change, and because of that, we are able to classify it like quite well.
Okay, thanks.
Any more questions? So thank you very much.